Download this code from codegive.com, link in the description below. Boosting Foliage Performance in Unreal Engine, a comprehensive guide. Foliage is a cornerstone of creating believable and immersive environments in Unreal Engine. However, its sheer density and the complexity of rendering thousands, even millions, of individual instances can quickly impact performance. This tutorial provides a deep dive into optimizing Foliage performance in Unreal Engine, covering various techniques with code examples and best practices. Understanding performance bottlenecks. Before diving into optimization, it's crucial to understand what's causing the performance hit. Draw calls. Each unique material or mesh requires a draw call. The more draw calls, the higher the CPU overhead. Foliage, often utilizing many instances of the same mesh with different materials, can easily generate a large number of draw calls. Overdraw. When objects are rendered on top of each other, the pixel shader needs to calculate the color for each pixel multiple times. Dense foliage, with overlapping leaves and branches, can create significant overdraw, increasing GPU load. Vertex count. More complex meshes with a high vertex count require more processing power to transform and rasterize. While individual foliage instances might be low poly, the sheer number of them adds up. Material complexity. Complex shaders with expensive calculations, translucency, subsurface scattering, custom lighting models, significantly impact performance, especially when applied to thousands of foliage instances. Shadows. Dynamic shadows cast by foliage are computationally expensive. Distance field ambient occlusion, DFAO. DFAO can be expensive for dense foliage due to its ray tracing nature. Physics. If foliage is physically simulated, example reacting to wind or player interaction, it adds to the CPU cost. Streaming. Loading and unloading foliage instances as the player moves through the world can cause hiccups if not handled correctly. Collision. Complex collision models on foliage can impact performance if the player interacts with them frequently. 2. Optimization techniques, a detailed breakdown. Here are various techniques to optimize your foliage, categorized for better understanding. Instancing and hierarchical instance static meshes, HISM. Instancing is the foundation of efficient foliage rendering. It allows the engine to draw multiple instances of the same static mesh with different transforms using a single draw call. Unreal Engine's hierarchical instance static mesh component, HISM, is the preferred method for managing foliage instances. YHISM. Draw call reduction. HISM groups identical meshes, drastically reducing draw calls. Culling. The engine can efficiently cull entire clusters of instances that are outside the view frustum or occluded by other objects. Memory efficiency. Only one copy of the mesh data is stored in memory, reducing memory footprint. Easy management. HISM provides tools for adding, removing, and manipulating instances. Implementation. One placement. Use the foliage tool in the landscape editor or programmatically create HISM components in your levels. 2. Adding instances. Use the add instance function to add individual instances with specific transforms, location, rotation, scale. 3. Updating instances. For dynamic effects, example wind, update instance transforms using update instance transform. Optimize these updates by only updating instances within a certain radius of the player or based on other criteria. Code example, adding foliage from C++. Blueprint equivalent. You can create similar functionality using blueprints. Add a hierarchical instance static mesh component to your actor, set the static mesh property, and use the add instance node in the event graph within a for loop to create multiple instances with random transforms. B. Culling techniques asterisk. Culling prevents the engine from rendering objects that are not visible, significantly reducing the GPU load. Frustum culling the engine automatically culls objects outside the camera's view frustum. HISM components leverage this efficiently. Occlusion culling the engine prevents objects hidden behind other opaque objects from being rendered. Unreal Engine uses various techniques, hierarchical Z, pre-computed visibility, etc., to perform occlusion culling. Importance volume for static environments, use importance volumes to prioritize occlusion culling in critical areas. Place an importance volume around the player's usual navigation area. Pre-computed visibility this technique is suitable for static levels with limited dynamic elements. It pre-computes which areas are visible from which locations and can significantly reduce overdraw. Navigate to build-lighting quality-build pre-computed visibility. Distance-based culling, LODs and culling distance. Level of detail, LODs create lower resolution versions of your foliage meshes, LODs, and configure the engine to switch between them based on distance. This dramatically reduces the vertex count for distant instances. Automatic LOD generation Unreal Engine can automatically generate LODs, but it's often best to manually create them for better quality and control. In the static mesh editor, go to LOD settings number of LODs auto generate LODs. Configure the generation settings, example screen size, simplification percentage. Manual LOD creation create lower poly versions of your meshes in a 3D modeling program and import them as separate LODs. Setting LOD distances in the static mesh editor, specify the screen size percentage at which each LOD becomes active. The lower the percentage, the further away the LOD will be visible. Culling distance completely cull instances beyond a certain distance. Use the cull distance property in the Foliage tool settings or the HISM component settings. Experiment with different culling distances to find the optimal balance between visual quality and performance. Per instance culling for more control, you can selectively cull individual instances based on custom logic. Use the remove instance function to remove instances beyond a certain distance or based on other criteria. Code example, distance-based culling. See Material Optimization Materials are a significant performance factor, especially with foliage. Simple shaders use as simple materials as possible. Avoid complex calculations, especially for distant foliage. Two-sided materials avoid using two-sided materials unless absolutely necessary. They double the shading cost. If you need to simulate backface lighting, consider using custom lighting in your shader instead of enabling two-sided rendering. Opacity mask versus translucency use opacity masks, masked materials, instead of translucent materials whenever possible. Opacity masks are significantly cheaper because they are either fully opaque or fully transparent, avoiding expensive blending calculations. However, opacity masks can introduce aliasing artifacts, so use them judiciously. Material instances use material instances to create variations of a base material without duplicating the shader code. You can change parameters like color, texture, and scalar values in material instances without creating a new draw call. Shared materials share the same material instances across multiple foliage types whenever possible. This reduces the number of unique materials and draw calls. Asterisk texture optimization asterisk. Asterisk MIP maps asterisk ensure that all your textures have MIP maps enabled. MIP maps are pre-calculated lower resolution versions of the texture, which are used for distant objects. This reduces the texture sampling cost. Asterisk texture size asterisk use the smallest texture sizes that still maintain acceptable visual quality. Power up to textures, example 256x256, 512x512, 1024x1024, are generally more efficient. Asterisk texture compression asterisk use appropriate texture compression formats. BC5 and BC7 are commonly used for normal maps and other textures, respectively. Asterisk shader complexity asterisk use the shader complexity view mode, accessible through the view modes drop-down in the viewport, to identify areas where shaders are overly complex. Simplify complex shaders by reducing instruction count, using cheaper math operations, and avoiding unnecessary calculations. Asterisk example material optimization, opacity mask versus translucency. Let's say you have a leaf material that uses translucency to create the effect of light passing through the leaf. Instead, you could use an opacity mask with a leaf-shaped texture. 1. Create a mask texture asterisk create a black and white texture where the white areas represent the leaf shape and the black areas are transparent. 2. Create a base material asterisk create a new material and set its blend mode to masked. 3. Connect the texture asterisk connect the mask texture to the opacity mask input of the material. 4. Set base color asterisk connect a color, or another texture, to the base color input of the material. 5. Adjust metallic/roughness asterisk adjust the metallic and roughness parameters as needed. This opacity mask material will be significantly cheaper to render than a translucent material, especially with many overlapping leaves. De-lighting optimization asterisk. Lighting significantly impacts performance, particularly with foliage. Asterisk static lighting asterisk if your environment is mostly static, use static lighting. Bake the lighting information into light maps. This eliminates the need to calculate lighting in real time. Build lighting only. Asterisk light map resolution asterisk adjust the light map resolution for your foliage meshes. Higher resolutions provide better lighting quality but increase build times and memory usage. Asterisk light mass importance volume asterisk place a light mass importance volume around the area where the player will spend the most time. This tells light mass to prioritize lighting quality in that area. Asterisk dynamic lighting asterisk if you need dynamic lighting, optimize the shadow casting. Asterisk shadow cascades asterisk reduce the number of shadow cascades. More cascades provide higher shadow quality but increase the rendering cost. In the directional light settings, adjust the cascade count. Asterisk shadow distance asterisk reduce the shadow distance. Only cast shadows for objects within a certain distance of the camera. In the directional light settings, adjust the dynamic shadow distance stationary light. Asterisk capsule shadows asterisk use capsule shadows for characters and other dynamic objects instead of complex mesh-based shadows. Capsule shadows are much cheaper to render. Asterisk disable shadows asterisk for distant foliage, consider disabling shadows altogether. The visual impact is often minimal, but the performance gain can be significant. In the static mesh settings, set the cast shadow property to false. Asterisk distance field ambient occlusion, DFAO can be costly, especially for dense foliage. Consider disabling it or reducing its quality if you are experiencing performance issues. You can adjust the DFAO settings in the project settings under rendering-global illumination. Asterisk specular highlights asterisk restrict the size and intensity of specular highlights on foliage, as they can contribute to overdraw, especially on translucent leaves. Wind and movement optimization *. Realistic wind effects on foliage are visually appealing, but they can also be performance intensive. Simple wind materials * use relatively simple wind materials. Avoid complex shader calculations. Global wind direction * use a single global wind direction for all foliage instances to minimize the number of calculations. You can pass the wind direction as a uniform parameter to your materials. Vertex animation * instead of simulating wind on the GPU using complex shader calculations, consider pre-baking animation into vertex data. This requires creating animations in a 3D modeling program and importing them as morph targets or skeletal meshes. Sparse updates * don't update the wind effect every frame. Update it less frequently, example every 0.1 seconds, to reduce the CPU load. Distance-based wind strength * reduce the strength of the wind effect for distant foliage. The impact of wind is less noticeable at a distance, so you can save performance without significantly impacting visual quality. Optimized wind actor * if you are using a custom wind actor, optimize its tick function. Only update the wind parameters when necessary. Avoid unnecessary calculations. Code example, sparse wind updates. Collision optimization *. Collision can become a bottleneck if your foliage needs to be physically interactive. Simple collision * use simple collision shapes, capsules, boxes, instead of complex convex collision or per-poly collision. Disable collision * for purely decorative foliage, disable collision entirely. Collision presets * utilize Unreal Engine's collision presets for foliage, example foliage, no collision. Overlap events * use overlap events instead of continuous collision checks whenever possible. Aggregated collision * combine multiple small foliage instances into a single larger collision object to reduce the number of collision checks. Async collision * perform collision calculations asynchronously to avoid blocking the main thread. This is more complex and requires C++ code. Streaming and loading *. Efficiently loading and unloading foliage is crucial for large open worlds. World composition * use world composition to divide your level into smaller tiles that can be loaded and unloaded independently. Level streaming volumes * use level streaming volumes to load and unload foliage based on the player's location. Asynchronous loading * load foliage asynchronously in the background to avoid hitching. Use the load package async function or the asset manager. HLODs, hierarchical level of detail use HLODs to merge multiple foliage instances into a single mesh for distant areas. This reduces the number of draw calls and simplifies rendering. Runtime virtual texturing, RVT consider using RVT for landscape materials, which can improve performance by streaming in textures on demand. GPU instancing *. GPU instancing takes instancing one step further. Instead of the CPU sending each instance transform to the GPU, all the instance data is stored in a buffer on the GPU. This significantly reduces the CPU overhead and allows for rendering a very large number of instances. Unreal Engine provides several mechanisms for utilizing GPU instancing. Instance static mesh, ISM, with enable mesh distance fields disabled * when using instance static meshes without mesh distance fields, Unreal Engine often falls back to GPU instancing for rendering, which is highly performant. Custom HLSL * for more advanced control, you can implement GPU instancing directly in your custom shaders using HLSL. This allows you to leverage GPU-specific optimizations. This is an advanced technique. 3. Profiling and debugging. Unreal Engine Profiler use the Unreal Engine Profiler, accessible through the window menu, to identify performance bottlenecks. The profiler provides detailed information about CPU and GPU usage, draw calls, memory allocation, and other metrics. Stat commands use the stat commands in the console to display real-time performance statistics. Key stat commands. Stat unit shows CPU and GPU frame times. Stat shows rendering hardware interface statistics, including draw calls. Stat scene rendering shows scene rendering statistics, including overdraw. Stat levels shows loaded levels and memory usage. Stat memory shows overall memory usage. Visualize tool enable the visualize tool, debug-visualize, and use options like shader complexity, mesh LOD coloration, and quad overdraw to gain insights into rendering costs. 4. Best practices. Start early. Optimize your foliage workflow from the beginning of your project. It's much easier to optimize as you go than to try to fix performance issues after your scene is already complex. Iterate and test. Continuously iterate on your optimization techniques and test the performance on your target hardware. Target hardware. Optimize for the specific hardware that your game is targeting. Lower-end hardware requires more aggressive optimization. Balance quality and performance. Find the right balance between visual quality and performance. Don't sacrifice too much visual quality for marginal performance gains. Use comments. Comment your code and materials clearly so that you and others can easily understand and maintain your optimization techniques. Document your process. Keep track of the optimizations you have performed and the results. This documentation will be invaluable for future projects. Keep up to date. Unreal Engine is constantly evolving. Stay up to date with the latest engine features and best practices for foliage optimization. Check the official documentation and forums. Conclusion. Optimizing foliage performance is an ongoing process. By understanding the performance bottlenecks, applying the techniques described in this tutorial, and continuously profiling and testing your scene, you can create beautiful and immersive environments without sacrificing performance. Remember to prioritize the techniques that will have the biggest impact on your specific project and target hardware. Good luck.